Welcome to Study Loop.
In this problem, we're going to talk about ideal gases and the first law of thermodynamics. So what we need to remember is that for an ideal gas, the pressure times the volume is equal to the number of moles times the ideal gas constant times the temperature. We also need to remember that for uh, an iso an adiabatic process, that is a process in which no heat is exchanged between the gas and the system, PV to the gamma is a constant quantity, where gamma is the adiabatic index. It's equal to Cp, the molar heat capacity at constant pressure, divided by the molar heat capacity at constant volume. And we need to know that gamma for a monoatomic ideal gas is equal to 3 halves, is equal to 5 thirds, while Cv is equal to 3 halves of R. Also, we need to know that the work done by a gas is equal to the integral of P dV, and that delta U, according to the first law of thermodynamics, the variation in internal energy of a system, is equal to the heat added to the system minus the work done by the gas. Okay? Also, we need to know that the variation in internal energy of an ideal gas is equal to the number of moles of the gas times Cv times the variation of temperature. So it depends only on the variation of temperature. If the temperature does not change, neither does the internal energy of an ideal gas. Okay, so what we have in our problem is a gas. We have 1.2 moles of a monoatomic ideal gas. Um, at a pressure, initial pressure P0 of 3.6 times 10 to the fifth pascals, at a temperature T0 of 300 Kelvin, and a volume we don't know, V0, and this gas expands to a final volume that is 3 times the original volume, so the volume triples. And it can do so by various paths. And we have to consider each one, and our goal is to calculate the work for each of these paths. So in the first path, we have to consider an isothermal process, that is a process in which the temperature is kept constant. And for this process, we need to calculate the work. So remember that the work is the integral of PdV, but for an ideal gas, PV is equal to nRT. So P is nRT over V. nRT is constant because T is constant in this case, and we have to calculate the work from the initial volume, which is V0, to the final volume, which is 3V0, of nRT divided by V dV. So this is nRT times the logarithm of 3V0 over V0. So this is N, which is 1.2 moles, times R, that's 8.31 joules per mole Kelvin, times the temperature of 300 Kelvin times the logarithm of 3, meaning that the work will be 3287 joules. Okay, this is the isothermal case. In question B, we have to consider the adiabatic case. In that case, no heat flows, and we know that PV to the gamma is a constant. So PV to the gamma is P0 V0 to the gamma. So P is equal to P0 V0 to the gamma divided by V to the gamma. The work is P, that's P0 V0 to the gamma divided by V to the gamma dV from V0 to 3V0. Um, so this is P0 V0 to the gamma. I'm going to write this actually as P0, V0 to the gamma times V to the minus gamma dV. So we can calculate the integral. It's 1 over 1 minus gamma times V to the 1 minus gamma from V0 to 3V0, meaning that W is P0 V0 to the gamma 1 minus gamma times 3V0 1 minus gamma minus V0 1 minus gamma. So the work is P0 V0 to the gamma 1 minus gamma, and I'm going to write what's inside as 1 over V0 gamma minus 1 times 1 over 3 gamma minus 1 minus 1. So notice that the V to the gamma here cancels, and we're left just with P0, V0, 1 minus, divided by 1 minus gamma times 1 over 3 to the gamma minus 1 minus 1. So W is P0. No, but actually, before calculating W per se, I'm going to calculate V0. We know that P0 V0 is equal to nRT0, and we know P0 and T0, so I can calculate V0 as nRT0 over P0. N is 1.2, R is 8.31 joules per mole Kelvin, T is 300 Kelvin, and P0 is 3.6 times 10 to the 5th pascals. So V0 is equal to 0.00831 squared meters. Okay, so W is P0, which I'm gonna just write the number. That's 3.6 times 10 to the 5th pascals, times 0.00831 squared meters divided by 1 minus gamma, so that's 1 minus 5 thirds, times 1 over 3 to the gamma minus 1, so that's 5 thirds minus 1 minus 1. So W is 2331 joules. Okay, then in question C, we have to calculate W if the process were isobaric, which means that the pressure would be kept constant. This is the easiest case of all because the pressure is constant, so we can just pull it out of the integral. This actually should be delta V instead of dV. P0 is 3.6 times 10 to the 5th, and delta V is 2 times V0 because it's 3 V0 minus V0. So it's V0 is 0.00831 as we calculated in the previous exercise, which means that W is 5,983 joules. In question D, we have to draw the PV diagram for each case and say in which case the absolute change in the work is greatest and smallest. So let's start by the isothermal process. Remember that P is proportional to 1 over V in that case. So it does something like, actually, it starts at P0, P0 like this. And then it decreases like this. So final value of PV. Um, this is the isothermal case. Then we have the adiabatic case. Remember that in that case, P is proportional to 1 over V to the gamma instead of just 1 over V. Uh, and in that case, P decreases a little faster. Okay. Sorry. Here we have the final volume of 3V0. Then, finally, we have the isobaric case. It's again the easiest case to draw because it's just a straight line. P is kept constant and V is changed from V0 to 3V0. Okay, and as we can see in our previous answers, the case where the work is greatest is the isobaric case, this one here. So is greatest for isobaric case. And it's the smallest for the adiabatic case. And we can easily see that from our drawings. Notice that the area here is visually greater than the area in the other two graphs. And since P depends on 1 over V to the gamma, then the area will be smallest in the adiabatic graph. In question E, you have to say for which process the heat exchange is greatest. So for the first process, notice that delta U is equal to 0 in the isothermal case because the internal energy of an ideal gas depends only on the temperature. So Q is just equal to W. So Q in the first case is equal to 3,287 joules. In the second case, in the adiabatic case, Q0, because that's the very definition of adiabatic. Okay, and then for the isobaric case, the situation is a bit different because Q is delta U plus W. Delta U is NCV delta T. Delta T for an ideal gas at constant pressure is equal to P delta V over NR. So N delta T is CV, NCV delta T is CV over R times P delta V plus the work, being that Q is equal to the variation in internal energy. That's actually, let me write this explicitly. It's 3/2 of R divided by R times the pressure, which is 3.6 times 10 to the 5th pascals. I'm not gonna bother writing the units. Delta V is 2V0, so it's 2 times 0.00831 plus our work, which is 2,331 joules. So the work, the heat is equal to the variation in internal energy, that's 8,975 joules plus 2,331, and this is equal to, actually, I'm sorry, this shouldn't be 2331. I just copied it wrong. It should be 5983. So it's 14,958 joules. Okay. So the greatest work, the greatest heat is for the isobaric case, and it's smallest for the uh, adiabatic case, as it should be. Okay, finally in question F, we have to see in which case delta U, the variation in internal energy, is greatest. So for the first case, for the isothermal case, delta U is Q minus minus W, but since the internal energy depends only on the temperature, the variation in internal energy is zero. For the adiabatic case, delta U will be just minus W because Q is zero, so it's minus 2331 joules. Actually, I wrote it as adiatic. It should be adiabatic. And finally, for the isobaric case, delta U, we calculated that in question E, that's 8,975 joules. So delta U uh, is greatest, the absolute value of delta U is greatest for the adiabatic case, and it's the smallest for the isothermal case. And this concludes our exercise.